right, so this next chapter is very important. Okay, in fact, if you normally in my normal classes, I spend 3 full lectures on this. Okay, so I'm going to spend the rest of today and all of, oh gosh, we're going to be covering chapter 5 for the next 3 weeks. It looks like, I guess. So in astronomy, we have a little bit of a disadvantage. Okay, everything we care about in this class is outside the orbit of the Earth-Moon system. In fact, most things are extremely far away, and we only have the ability to visit some things in our solar system. But when it comes to stars and galaxies, we can't visit them. So what we have is we are sort of forced to just accept what these things give us. And 99.9% of what we get from stars and galaxies come in the form of electromagnetic radiation, which just generically is referred to as light, right? Just light. And so obviously we're going to have to understand as much as we possibly can about the properties of light, how it's emitted, how it travels through space, how we collect it, how we analyze it. Okay, that's why we're spending so much time on chapter 5 here. So there's different types of light. We are going to distinguish between 7 different types of electromagnetic radiation. Gamma rays, X-rays, ultraviolet, what we call the visual part of the spectrum, which sometimes is just called optical or visual, infrared, microwaves, and the radio part of the spectrum. So these things are all identical in nature. Okay. There are some differences in the amount of energy they have, but there's a lot of things very similar to them. I mean, it's like saying these are all Skittles, right? But they're just different flavors of Skittles. It's kind of like that. So we characterize light by a number called wavelength. Okay? And we measure wavelength in typically nanometers. Sometimes you might see the unit of angstrom, but nanometers is a billionth of a meter. Okay? And as far as visible light is concerned, visible light lies in the range of 400 to 700 nanometers. Now, we have this characteristic length for light, but you should refrain from trying to attach some physical length to light. It doesn't have a physical length. It has wave properties, and waves have a characteristic length to them. And so I'm not saying that light is actually this long, but it has behavior as if it is like this long. For example, when light interacts with particles or molecules that are similar in size, they interact a lot, scatter and things like that. But for the most part, kind of divorce the idea of light having any kind of length to it, but it has this characteristic wave property though. You want to really know the numbers down here, 400 to 700 nanometers. Okay, 400 to 700 nanometers. What we call different wavelengths of light is seen as different colors. So when I say the different wavelengths, we mean colors. The 400 nanometer end is called the blue end of the spectrum. That's where purplish, bluish light is found. If you go beyond 400 nanometers, you go into the ultraviolet. Okay. The 700 nanometer part is, we call it the red end of the spectrum. Okay, that's where all the reddish light is. If you go beyond that, you go to the longer wavelengths, which is the infrared. Okay, the human eye is designed to view light from approximately 410, 420 nanometers. If you try to go shorter than that, the eye has a difficult time getting that light. What we're going to see a little bit later is the lower in wavelength you go, the more energy light has. And the rods and cones in your eye that receive light and send signals to your brain are not very receptive once the light becomes very energetic. In fact, if it becomes too energetic, it just starts to blow your eyes out. It just destroys the cells in your eyes. So that's one of the reasons why it's bad. The longer wavelength portion, the red light, that varies a bit based on the person. For most people, it's around 700 nanometers, but there's some freaks that can go all the way to like 750, close to 800. They can see a lot of the infrared. It's very faint, though. The problem with that is your eyes are very sensitive, but the energy of reddish light is very low. And so it's not able to stimulate the cells that are in your eyes. And so it just all depends on different people's eyes. Some people's eyes are more sensitive. They can see, further into the infrared. But for most people, it's 400 to 700 is the range you see. Yes. Sure. Yeah, so 400 is the blue end of the spectrum, 700 is the red end of the spectrum. And you really want to know those numbers because while there's different types of electromagnetic radiation, we're always going to go back to reference how everything compares to what the eye can see. Okay, and we're interested in the light that the eye can see, not just because we see that light, but the atmosphere is transparent at those wavelengths. Light can get through the atmosphere from space, and so astronomy originated by looking at the stars through the wavelengths that we can see with our eye. All right, so light can also be characterized by a frequency, which is another wave-like property. We're really not going to ever discuss light as different frequencies. That's kind of beyond the scope of what we need to do in this class. But there is a relationship between the two things, the wavelength and the frequency. When you multiply those numbers together, you always end up with the same number. The wavelength times the frequency of light always results in the same number. We call it c, which stands for the speed of light, and it's 300,000 kilometers per second, which works out to about 186,000 miles per second. Yeah, 186,000 miles per second. And that is the speed at which light moves through space. Okay, and all forms of light, gamma rays, X-rays, all the way through to the radio part of the spectrum, everything travels the same speed. Okay? The lights in this room, the radio waves coming from radio stations on the hills, okay, X-rays in the dentist's office, everything moves at the exact same speed. Okay, which may seem like a simple fact. The problem is that we will see light in different contexts, and it will certainly seem like there maybe is different speed involved because there's very different energies involved. Gamma rays and X-rays are very high energy phenomena, potentially very dangerous radiation, whereas something like radio waves are virtually harmless, but they have a lot of similar characteristics, and speed is one of those things. So that's nice. When we study objects in space, all of the light that stars and galaxies emit, we receive it at the same time. There's a look-back effect, but it would be nuts if things moved at different speeds based on wavelength, and life would be very chaotic. All right, at least astronomy would be. All right, so this gives us at the top here, this gives us the relative wavelengths of light. And so the order is important here. Visible light is right in the middle of the spectrum, 400 to 700 nanometers. We have three wavelengths that are shorter, gamma ray, X-ray, ultraviolet, and we have three wavelengths that are longer, infrared, microwaves, and all the stuff at the end here, that's all referred to as radio waves. Okay. So radio waves. The graph at the bottom is a graph of wavelength and atmospheric transparency. Okay, and so what you're looking at here is this. At the very top of the figure is light from space, and the arrows go down, and if the arrows reach the bottom, that means that light can penetrate through the atmosphere completely. But if the arrows only get part of the way down, that means at some point in the atmosphere, that light gets absorbed. Okay. So you can see things like gamma rays and X-rays, for the most part, don't get through the atmosphere, which is good because that stuff is very harmful to a human. A lot of ultraviolet doesn't get through. Close to the visual part of the spectrum, you do have light that can get through. So right over here, this area right here, a lot of light can reach the ground in part of the ultraviolet part of the spectrum. So there is, that's why there's a danger in sunburns and being outside for long periods of time, because you do get some ultraviolet light. The really harmful stuff is blocked, but some does get through. There's a window here in the visual part of the spectrum. Okay, so all the light that we can see with our eyes, that gets through. A lot of infrared gets not through the atmosphere, but can get very far down. This level right here would be this little bump you see here next to the visual part of the spectrum. That's around 10,000 feet. So if you're up above 10,000 feet, you can actually get a lot of the infrared spectrum. When I did all my work at Keck in Hawaii, it's a mountain that's above 10,000 feet. I did infrared astronomy. You can see beyond 700 nanometers. We can go all the way into around 2.5 or 3 microns, which is, you know, it's a few ways. It's not that far into the infrared, but you can do a lot of work there. Okay, and then there's another window, the radio is part of the spectrum. Okay, a lot of radio waves get through. Right. Now, if you're going to observe the other stuff, stuff that reaches the ground, obviously you can have ground-based telescopes. So we have radio telescopes and visual wavelength telescopes in the ground. For other types of light, you need to be at either a higher elevation or you need to be in space. Some ultraviolet, a lot of infrared, can be done in mountaintops or in plains, actually. We actually have an observatory here in the Antelope Valley that's called Sophia, and it's a plane. 747 that's been converted into an observatory. Flies up real high, 55,000 feet. Flies up for, you know, all night, and it can observe a lot of the infrared because it's above a lot of the effects of the atmosphere. But things like X-rays, that's got to be done in space. That stuff, none of that stuff gets through. All right. Any initial questions about this graph or this information here? All right. So, question for you: which of the following lists of wavelengths is correct in order of increase in wavelength? That means as you go through the list, the wavelength should be going up. It should be increasing. All right, well, I see a lot of A, but I do see a bunch of other stuff out there. But it is definitely A. Okay. So, at a bare minimum, you need to know that that blue is shorter than red. You can associate blue with ultraviolet. You can associate red with infrared. But at a bare minimum, know that blue is shorter than red. That's really key. In fact, ideally, you'd want to know the full sequence. Visuals in the middle, know the 3 things that are shorter and 3 things that are longer. But remember, blue is shorter than red. That's important. Right, so another thing we can do with light is light has properties where it acts like it's a particle. Okay, so waves have a lot of features to them. Waves can do a lot of things. But light has a particle-like property to it. Okay, and what I mean by that is you can do things with light that you can do with an object that you can. I mean, give you an example of this. You can reflect light. Okay, that's like bouncing off of a surface. That's like a ball being bounced off a surface. In fact, one of the important findings of early part of last century was something called the photoelectric effect. People discovered that if you shine light on a metal, you can actually create an electrical current by shining light on the metal. Okay? We actually found that if you shine light on an object with enough intensity, you can actually cause the object to move. You can push it. That means light has energy associated with it. Okay? So these effects, these are all particle-like effects. Light has an associated energy to it, and that energy is related to the wavelength of that light. Now, what this means here, this terminology here, is saying that the energy of a particular wavelength of light is inversely related to that light. Okay? So what that means is if you're looking at light with a very short wavelength, it has a lot of energy. Small wavelength, large energy. So things like X-rays, gamma rays are the shortest wavelengths of light, therefore they have the most energy to them. Okay. That means longer wavelengths of light have very low energy. Radio waves have very low energy. That's why it's very easy to create very powerful radio signals and have them travel long distances, because it doesn't require a lot of power to produce a radio signal. Okay, and unfortunately, we don't have giant towers emitting X-rays all throughout the atmosphere to broadcast information, because X-rays, not only are they bad for you, but they'd be very difficult to produce, an X-ray signal that can be read throughout an entire valley or something. Anyway, yeah.
Would a light on a mirror create energy?
Yes. So I mean, obviously, you could do things like if you shine light that's intense enough, you can heat up something, right? I mean, everybody took the magnifying glass and burnt leaves or ants or whatever. That's a good example of doing that. You can start a fire by focusing light. So there's energy associated with that. Yeah. But I mean, one of the designs, actually what's interesting, one of the designs we have for more advanced propulsion in space is called solar sail. What you do is you have this gigantic sail, basically, and light shines on it. And when it shines on it for enough time, it will cause the object to accelerate. It's a force, basically. And so that is a design that they have. Giant solar sails, you can extend them, pushes on the sail, causes the spaceship to accelerate, and then you just put the sail down, and that's it. That's definitely one of the... And actually what's interesting about that is there's been a proposal to travel to Proxima Centauri with spacecraft that are basically the size of a smartphone. They're just real small. It's all robotic. It's the size of a smartphone, but it would have a giant sail on it, and because a smartphone-sized object would have virtually no mass, it wouldn't take much to accelerate the object. So solar sails are great ideas when it comes to small things. Because how do you put fuel or propulsion on an object that's super tiny, right? The best way to do it would be with the sail. So that's kind of interesting. All right, yeah, so energy with light. Now, I want to make one distinction here because these are seemingly similar terminology here, but energy does not mean intensity. Those are different things. Okay? When we say the intensity of light, we're talking about the amount of light. Okay? So objects that have intense light simply are very bright. But that doesn't necessarily mean there's a lot of energy. Okay? It just means it's very bright. All right, so what would be now the correct list of wavelengths in order of increase in energy? What would that be? Yeah, so as you go down the list, the energy should go up. As you go down the list, energy should go up. All right, everybody's saying D pretty quickly. That's good. All right, so it's reversed. It's reversed. Okay, infrared's shortest. I'm sorry, infrared is the longest wavelength, so it's the smallest energy. Okay, good. And again, same thing. You want to know the pattern. Red is a shorter energy, smaller energy than blue is. So the order that you know for wavelength, you just switch it. All right, good. All right, so what do we do with starlight? Right, here's what we want to do. Now we know a little bit about, yeah, Dakota. Yeah, so radio being the longest wavelength has the lowest amount of energy. So the order that we have for wavelength here, you can just do the very opposite to get the energy order here. So over here, energy is the lowest and it increases as you go down. Gamma rays being the highest energy. So actually, let me give you one example before I actually move on from this. But so when we look at objects in space, one of the things we really care about is what type of light is primarily being emitted by the object. It tells us a lot about what's going on. Okay, for example, our sun is a little more than it's very close to 10,000 degrees Fahrenheit. An object that's 10,000 degrees Fahrenheit that's dense like the sun primarily produces visual wavelength photons. Okay? So that's a moderate thing. I mean, it's not too energetic. Clouds in space that are very dark and cold emit lots of radio waves. Some infrared actually, a little warmer. Things like X-rays. X-rays are emitted by more violent phenomena, higher energy things. Like, for example, we typically detect black holes because objects that are falling into the black hole are spewing out tons of energy as they fall in. And so we primarily detect black holes through X-rays that are being spewed out. Gamma rays are the highest energy phenomenon. It's the most violent, dramatic things in the universe emit that stuff. When two stars collide or something like that, sometimes that can produce a gamma ray burst. When a massive star explodes as a supernova, it's a gamma ray burst. So it's sometimes knowing the type of light that's being emitted is indicative of what kind of thing is going on there. And that's why the energy is important for that. All right. So for sunlight, we know the different types now. What we do with it? Well, there's actually very little that we cannot learn about a star based on the light we get from it. We can determine from the light we get from stars and galaxies what the total energy output of that light is. Okay. We call that luminosity. We can determine the temperature of objects based on the light that we get from them. We can infer the size of the object, not because we see the size, but you can constrain how large an object is based on how hot it is and how much light it emits. So we can actually figure out sizes for stars. We can determine what kind of elements exist inside the star, and we can determine a lot of things about an object's motion. You can detect motion from studying light. Called Doppler shifts. You can determine how fast things rotate, how fast things travel in space. And then obviously, if you can see the object, you can determine some things about distance for some of these. In fact, there's very little that we don't know about a star based on the light we get from it. Very little we don't know. And oddly, though, I guess I should say ironically, the two bits of information that we can't directly get from studying starlight are probably the two most important things about a star. And that's the star's mass and its age. It's very hard to determine for a single star based purely on its light how massive it is or how old it is. You can infer it in some ways, but it's not as... See, all the things that are up here are very easy measurements. Okay? It's a simple measurement with a simple instrument, and you can figure out all these things very easily. The other stuff's a little harder. Okay? Now, what we want to do, though, is while we can get all this information, the question is how? How do we get this stuff? How do we know how to do that? Well, this picture here, when we capture light from objects in space, we do it in one of two ways. Primarily, one of two ways. One of the ways is this here. This is called a spatial image. Okay? For a spatial image, we have spatial information. You can see the distances of things here. You can see the size of things. You can get colors, but colors a lot of times are sort of blended together. This particular image was not that way. See, what the eye sees, the eye has spatial information, and it has some spectral information. You can see colors for things, but you don't really know much about what those colors are like when you sort of dissect them. I mean, like, for example, it's not obvious that light from the sun is a rainbow of colors. When we see sunlight, we sort of associate with sunlight yellow color, right? But there's blue and green and red and all kinds of colors in starlight. But the combined effect of all that color is to give you this whitish yellowish appearance. That's not obvious. The eye can't distinguish that. When it comes to spatial images, the same thing. We see colors here, but that just means that may be just the dominant color. There could be other colors there. There could be green in this, but you can't tell. Okay, in fact, actually, this particular image was taken in a special way. These were taken with filters that only allowed blue, the reddish pinkish light, and this orangish one through. And it blocked out the other light. So this particular image is not a great example because while it's a spatial image, there's some spectral information. Now, it turns out that most of the information we get from space is not from stuff like this picture. Okay, and this picture is very easy to interpret. The human eye can see these things, right? But it's a little deceptive. You don't see the same stuff when you look at objects in space. If you actually were in space with just your eye looking at things, you never will see things like this. The level of light in space is so low that you would never see most of these things we see in images. Anyway, we don't get much information from pictures like this. What we do is we generally get information that looks like this. This is called a spectral image. It has no spatial information. Okay? We cannot tell the size of objects. We can't tell how they're spaced apart. What this would be like taking, say, the center star in this image here and just capturing the light from simply that object, and we dissect it. We basically break it into its individual wavelengths, and we study what goes on at different parts of the electromagnetic spectrum. This particular picture here, which looks bigger here. Okay. This is a spectral image of our sun. Okay, so there's no spatial information here. All we're doing is we're taking the light from the sun and we're breaking it up so we can investigate what's going on in individual wavelengths in the visual part of the spectrum. Okay, at the top here is 700 nanometers. At the bottom is 400 nanometers. Okay. And so what this actually is one long continuous spectrum, but what they do is they break it up and they stack it like this. So it's a technique that they use so you can fit it all in one nice image. Otherwise, you have this long line. But there's a lot going on here, right? I mean, if I showed you a spatial image of the sun, what do you get? You get this big ball that's yellow, and that's it. Nothing very interesting. Spectral images have a lot more information. Okay, what's going on in this image here is every single dark line that you see is the result of an interaction between light and an atom in the atmosphere of the sun. And every single interaction says something about the nature of the sun. Okay, I mean, the fact that the lines are present tell you that certain elements are present in the atmosphere of the sun. Some of the stronger lines mean that there's more of that element compared to another one. The thickness of these lines a lot of times reveal information about how the object moves. So the idea is we really need to know how an image like this is made. In order to understand that, we have to understand interactions between light and atoms, because that's what this is all about. Okay? The rainbow of colors that you see here come from the surface of the star. They have to pass through the atmosphere. When they pass through the atmosphere, that's when all the dark lines appear. Okay? But all of that contains information. And so we really have to understand how this is made, and then we can, once we learn how it's made, then we can figure out how to extract information out of it. And the vast majority of astronomical research is done in this way. It's through spectra. It's analyzing individual wavelengths of light and see what's happening there. Okay, so this is what we have to do. We have to go through this thing. Right. Any initial questions about that idea? All right, so let's do it. The way we're going to do this is we're going to start simple here. We're going to talk about the structure of the atom, and then we'll talk about how light can interact with it. So I'm going to give you a really basic review of the structure of atoms. I say review because all of you should be familiar with this, because you've taken, basic chemistry at some point. And so this will be, but the model that we're going to use here is about as simple as I can make it. I can't really make it any simpler than this. So we're going to take what we call the Bohr model. Okay, a really simple model where there's a nucleus and there's electrons flying around. Okay, picture on the right here is the hydrogen atom. Okay, it has a single proton in the center with its nucleus, a single electron that we say orbits the nucleus. Okay. In fact, actually, the electron exists in a region that surrounds the nucleus called the electron cloud. It's a probability cloud. It means the electron can be found anywhere in this cloud. It doesn't necessarily orbit, like spin around. I mean, you could treat it that way, but it doesn't necessarily do that. Now, this is your standard atom. 92% of the universe is this atom right here. 92% of the universe. Actually, 92% of the visible known matter of the universe is this, which means it's only like 4%. Most of it's dark matter and dark energy and things like that. But, all right, anyway, now when it comes to atoms, the size of an atom is determined by the electron cloud. That's how big it is. When atoms interact, it's because electron clouds touch each other. The mass, though, is all in the nucleus. The nucleus determines the mass of the object, because the proton has like a mass that's almost 1,000 times the mass of the electron. So that's really the mass of the object. Now, the picture I drew here is not to scale. Okay, the electron cloud is much too small. Okay. However, let me give you the numbers here. So this is a scaling question like we did in the very first chapter. The proton has a diameter of 1.6 times 10 to the minus 15 meters. The electron cloud has a diameter of 4 times 10 to the minus 10 meters. Okay, so what we're going to do is this. We're going to scale up the atom. Okay, so we're going to make the proton the size of a basketball. Okay, and based on the numbers that you see there, do you have any idea how far away you'd have to place another basketball to put this thing to proper scale? Okay, so think about that for a little bit. We'll have you take a vote on that. All right, what do you think? Let's see a letter here. Well, I see a lot of B's and C's. So that B's and C's are on the right track here. The answer ends up being C here. Okay, so why? Well, if you look at these two numbers, the size of a proton is 10 to the minus 15, and the size of the electron is 10 to the minus 10. Okay, there's 5 orders of magnitude difference between the two numbers. 5 orders of magnitude. That's a factor of 100,000. Okay, so what it's saying is that the electron cloud is approximately 100,000 times larger than the proton. So the proton's a basketball, which would be about a foot across. The electron in the electron cloud would be about 100,000 feet away. So what's 100,000 feet away? 5,000 feet is about a mile, so we're talking about tens of miles. Okay? In fact, if you actually do the numbers, because I mean it's not exactly 5 orders of magnitude because you have a 4 and 1.6 here, but if you actually work it out, it comes out to be around like 70 miles. Okay, so if I'm holding a proton in my hand, the electron cloud would extend all the way to Victor Valley, downtown LA maybe. I don't know if it gets all the way. Yeah, I get down there. Downtown LA, Bakersfield. It'd be pretty big. Which, by the way, is the same scaling for like the solar system. You could fit the sun in this room here, and the solar system would fit in Southern California. Similar thing. All right. Great. All right, so let's talk about the nucleus. There's 2 parts to the nucleus. You have protons and neutrons. Protons are important. We have a periodic table in here, yeah, over there. So that periodic table is organized by protons. How many protons are in there? And different protons refer to different atoms, totally different chemical properties to them. The names for atoms are dictated by the number of protons they have. Protons are positively charged. They attract the electrons. That gives structure to the atom. Neutrons, however, are neutral. They do not have an electrical charge. They're part of the atom. They help keep it together. But if you change the number of protons, you totally change the atom. If you add or subtract protons, you got a totally different atom. You can add protons through a fusion process, which is how stars work. That's how stars get their power. You can typically take away protons by either a fission process, which is not very common in the universe. Most protons are removed through radioactive decay. So that's that. That's protons. Pretty simple. Now neutrons, you can vary the number of neutrons for a given atom. Okay? For example, carbon has 6 protons, always. If you change that, it's not carbon anymore. Now, most carbon has also 6 neutrons. That is the most stable, most abundant form of carbon, but there are other types of carbon. You can have carbon-13 or carbon-14, okay, which has extra neutrons in it. They're less common. Sometimes if you add too many or take away too many, you make the atom unstable. Okay? Carbon-14 is the basis for radioactive dating for carbon. It has a half-life of thousands of years. It changes into carbon-12 eventually. Okay? So change in the number of neutrons, we call that different isotopes. Okay? It's the same atom, just different number of neutrons. Okay? When you drink water, for example, water is an oxygen atom and 2 hydrogens. But something like 1 in every 10,000 or so water molecules contains a deuterium atom, which is an isotope of hydrogen. Okay, deuterium is hydrogen with a neutron thrown in there. Okay? But if you have a big glass of water, you're drinking a bunch of deuterium, which is okay. It's not harmful. It's water. It behaves like water, tastes like water. You'd actually have no idea, unless you drink a lot of it, is there any difference. I mean, if you drink water that was pure deuterium, 2 deuterium atoms and an oxygen, it would taste delicious going down, and then you slowly die. Because your body works chemically. So you drink, we call the stuff that's made, so there actually is water like this. It's called heavy water, okay, not hard water. Hard water means high mineral content. Heavy water refers to water that's made with deuterium as opposed to hydrogen. And when you drink it, your body believes that it's standard water because it thinks chemically. Okay, it works chemically. So it sees protons and stuff and it reacts that way. But there's some functional differences here. Okay, deuterium weighs twice as much as hydrogen. It's also slightly larger. So your body starts to do things with it, starts to put it in places where water goes, but it doesn't fit. So it just puts a lot of stress on your body. I mean, when you drink this stuff, I mean, kidney failure, heart failure, a lot of things happen. Yeah.
Isn't the heavy water what they use for nuclear bombs?
It's very common in nuclear testing and things like that. I actually had to work with this stuff because I worked for this instructor that was a little crazy when I was an undergrad. He believed in the process called cold fusion. And what cold fusion is taking deuterium water and shoving it inside these metal lattices. And the idea is you can shove enough in there, you can cause them to fuse together at low temperatures. Again, it was very controversial in the 90s. There was this huge fiasco about it. And he's really tried to get it to work. Anyway, but it is common things in nuclear reactors. The water that's used, yeah. All right, anyway, every atom has isotopes. Now, hydrogen is special, okay, because most isotopes are simply given a name, that's the name of the atom, and a mass number. So like carbon-13 is just 6 protons, 7 neutrons. That's it. But hydrogen is special because we actually give different names to the isotopes. And that's confusing at first because people believe they're different elements. They're not, though. So deuterium and tritium are both hydrogen. Properly, they should be called hydrogen-2 and hydrogen-3, but we give them these common names, deuterium and tritium. Deuterium is pretty common. Like I mentioned, 1 in every 10,000 hydrogen atoms is actually deuterium, mostly harmless. Tritium is very rare. It's usually a result of some kind of radioactive incident or something, and decays rather quickly. Anyway, so now that's it for the nucleus. That's as complicated as I can make it. I mean, if we took a higher level class, I couldn't make it more complicated. So all you got to know out of this is that when it comes to the nucleus of the atom, protons determine the type of atom. Different neutrons are simply isotopes. Same atom. Okay? Same chemical properties. Just a little difference in mass and size. Now, I'm going to return to the nucleus later because stars derive their energy from manipulating the nucleus of atoms. They can rearrange things. They can put pieces together. They can take pieces apart. And that's not chemistry. That's nuclear physics. That's a totally different thing. And so in a few lectures from now, we're going to get into nuclear fusion. And so knowing the nucleus is going to be important for that. For what we're doing today, we care about electron clouds. Okay? We care about what the electron does. Because when it comes to how light interacts with matter, it has to do with electrons. Okay, this is where all the good stuff is. Okay, this slide is really important. Really important. Everything on here is really important. Yes? No. This is actually, this material here is going to be on the next test, not the one that gets. Yeah, at the end. We have to sit through this, sorry. All right, anyway. So let's go through each point here. The number of electrons in an atom normally matches the number of protons. All right, so you've got carbon, 6 protons, 6 electrons. Wow. The electrons orbit the nucleus in the electron cloud, but they are restricted to very specific radii and energies. Okay, this is an important point. This is what atoms are like. Electrons are not free to be wherever they want to around the atom. They are restricted. They can only be in certain levels, basically. Okay. This is different than the way we're used to the world working. Most of the world, as we experience it, is continuous. I'm able to stand anywhere I want to in this classroom. I could sit in any desk I want. I can move the desk to any location. If I were an electron, It wouldn't be this way. I can only stand in certain places. I can only be in certain desks. I couldn't move things around. Okay? That's the way the world works on a micro scale. This is a fundamental aspect of the micro world. This is what quantum mechanics is all about. Quantum means quantized, comes in parts. Okay, it's discrete, not continuous. We don't know why the world's this way. Okay, that's just the way the world works on a macro scale. Electrons are in these levels. The structure of the levels are determined by how many protons there are, because the protons attract the electrons. So the structure of these levels determine how many protons are in here. And therefore, each atom has its own unique structure to its levels. Hydrogen looks a certain way. Helium has a slightly different structure to it. Has levels 1, 2, 3, 4. Okay, but the levels are actually more tightly bound for helium. And so this is nice. Each atom has its own pattern of lines. And we actually call this the fingerprint of the atom. Okay, this is how we tell different atoms apart, by the differences in these lines here. All right, so let me ask you a question about these levels, because we know that if this is hydrogen here, we got a proton sitting in the middle here, and we got an electron that can be, really, it's only one electron, and it can be at any one of these levels. There's more levels, there's 4 and 5 and 6 and so on. But if we talk about the electron's energy in these different levels, what do you think is the correct relationship here? Okay, what do you think? Think about that for a little bit. So tell me your feelings about this. All right. Don't think too much about it. Let's see what you think. What do you think? All right, so, I don't know if there's a dominant letter out there. There's equal A's and B's out here, actually. Okay, so let's put it this way. Before I actually show you it, proton sits here in the center, and the electron, what, is it attracted to the nucleus? Is it repelled by it? What's going on here? Attracted, okay? So this is very similar to gravity, right? Imagine the Earth is a nucleus, and I have my clicker here, right? If I let go of this, what's it going to do? It's going to fall, right? Because it's attracted. It wants to be down. Okay? We actually describe this clicker as having different levels of energy based on how much it can fall. We call this gravitational potential energy. A very similar thing applies here because there's an attraction. If the electron was free to do whatever it wanted to do, it would be down here in level 1. So it can be the closest it can to hydrogen. But if you excite it, the electron, if you give it energy, okay, you can move it to higher levels. Okay, but if I want to move the clicker to higher levels, what I have to lift it, right? I have to put energy into it to lift it to a higher location. Same thing with the electron. So the levels look like this. The first level is the lowest energy level. And as you go up, the energies increase because it's harder to move the electron to these levels. It requires energy to push the electrons up. Okay, so imagine it's like lifting an object in a gravitational field. You have to put energy into it to do that. So energy is required to lift things up, and energy is released when things fall down. Okay, that's how the energies work. All right. So how can you do that? How can you give electrons energy to move them up? Well, what we talked about earlier in the class was photons have energy. Light has energy. And light can impart its energy to the electrons and move them to higher levels. We call this photon absorption. Okay? It's photons being absorbed and having electrons move to higher levels. Okay? Electron can be kicked into a higher orbit when it absorbs a photon with the exact right amount of energy. That's important. If you want to move an electron up to a higher level, it has to receive the perfect amount of energy to make that move. It can't be too much. It can't be too little. Okay, the way you should think about this is like walking up a flight of stairs. Okay, if you don't take a high enough step, you're not getting to the next step. Okay, but also you can't take a step that's too big. Okay, the way that this works, the step has to be perfect. You have to take the perfect. Now you can go 2 steps at a time or 3 steps, but the level you lift your leg has to be exactly right. If you don't lift your leg up exactly right, you're not moving at all. That's what's happening here. you have to have the exact energy that corresponds to the energy difference between the levels. If you don't do that, there's nothing that's going to happen. Okay, so the photon gets absorbed. It gets removed. It gets taken out of the light. And that energy goes into making the electron go to a higher level. Okay. Any other photon that does not match up with the energy differences here will not interact with this atom, will pass right by. So there's only a small set of wavelengths that work with the atom. That allows things to interact. The other wavelengths don't work at all. All right, so a couple more questions here. We'll wrap this up. Which pair of orbital levels seen to the right has the largest energy gap? Okay, so we talked about level 1 being the lowest, 2's higher, 3's higher, but in terms of the energy difference between them, which has the biggest energy gap? All right, so I think I see more C than anything else, which is good. So the largest physical gap is the largest energy gap. Okay, so the longest distance is from 1 to 4. That's the biggest gap. Okay, great. Okay, so this is the kicker here. This is the question. You get this question, then you get what we've been talking about for the last half an hour. Okay, so I'm going to describe here 2 different transitions that can happen. Okay, you can take an electron that's down here in level 1 and you can move it to 2. Call that 1 to 2, or go 1 to 3. Okay. Now we've already established from the last question that 1 to 3 requires more energy because it's a bigger gap. Now I want to ask you, what would be the correct wavelength relationship between the 2 photons? Okay. So I want to compare the wavelength of the photon that takes me from 1 to 2 and compare that to the one that takes me from 1 to 3. Okay, so think about that for a moment. Think about the energy involved, how that has to correspond to the wavelength. What would that be? Wait, what do you think? Real high. Most you're saying B. Okay, that's not right. All right, so let's talk about it. 1 to 3 has the largest energy gap, right? So it requires the most energy. Yes? Okay. What do we know about photons, wavelengths with a lot of energy? Are they long or are they short? They're short, right? So when you're looking at this relationship here, the wavelength that takes you from level 1 to level 3 has to have more energy, so therefore it must be a smaller wavelength. Okay? The wavelength that takes you from 1 to 2, it's less energy, so it is longer. Okay? It's this tricky thing about the relationship between energy and wavelength. It's an inverse relationship. More energy needs a shorter wavelength. Okay? So if the wavelength, let's say from 1 to 2 is, I don't know, let's just say it's red light, then the one from 1 to 3 would have to be shorter, so it might be, I don't know, yellow light or green light or something like that. But that's really the key to understanding this stuff, that every atom has this structure. Every atom has these transitions. So every atom has basically a set of wavelengths that correspond to it that allow electrons to jump around. Okay, now let's go all the way back here. All right, so when light is generated from the surface of the sun, it is a rainbow of colors. Okay, it would be, you'd see no dark lines, you just see colors. Then that light has to pass through the atmosphere. There are all sorts of elements that exist in the atmosphere of the sun. And a lot of the wavelengths of light that are trying to get through are wavelengths that the atoms like. And every single dark line that you see here is due to a photon absorption. Every single dark line is a result of a photon being captured by an atom and being absorbed and having its electrons jump to higher levels. Okay? So what you're seeing here is the combined result of all the various elements that exist inside the sun. There are lines due to hydrogen here, sodium, magnesium, there's potassium lines, calcium lines, there's carbon lines and helium, and there's all kinds of elements that exist inside the atmosphere of the sun. And each atom has a set of wavelengths that it works with. So you're seeing, hundreds and hundreds of lines, but it all corresponds to different elements and different transitions. And so this may look really complicated and messy, but we know from laboratory experiments how every single element looks. We know what to expect. For example, this line up here, and this line right here, and this line down. What are the lines? I don't know which one it is down here. But up in red, in this kind of like greenish blue area, and down here in the blue, those are lines that work for hydrogen. There's 3 lines that correspond to the hydrogen atom that exist in the visual part of the spectrum. We know where those are. So we know that those are the hydrogen, and then we can kind of subtract them out and look at the rest of the lines. And then there's a pattern that works for calcium. We know which ones those are, take those out. And so we can dissect each individual line. We know exactly where all the lines come from. So that's where most of this information is from. Ooh, what happened here? All right. All right, so in particular, here is the hydrogen atom. Now, ignore for the fact that you see arrows going down. I'll talk about that in a moment here. This is what hydrogen looks like. This is the structure of it. This is level 1, 2, 3, and so on. And the wavelengths that you see listed here are the wavelengths that correspond to each transition. So every single possible jump that you can make has a wavelength that goes with it. Okay? So level 1 to level 2. Okay? 121.5 nanometers. So if a 121.5 nanometer wavelength of light, which is an ultraviolet wavelength, passes by a hydrogen atom, it has the ability to be absorbed, and an electron will jump to level 2. Okay. You see in these series of lines up here that we call the Balmer series, this is level 2 to higher. So it's level 2 to 3, 4, and 5. These 3 lines, 656.3 all the way down to 434, those are the only 3 lines in the hydrogen spectrum that shows up in the visual part. Okay, everything else is either an ultraviolet wavelength or it's an infrared photon. In fact, you've actually seen these colors here. In fact, my laser light is the first wavelength. Okay, my laser light's red. 656.3 is this light. Okay. Now, it's not because there's hydrogen in here. It's just the way they made this thing. They just make it so it matches up with red light. But if you blend together those 3 colors, and I can show you what that looks like. We saw that in an earlier lecture. I show you this picture of the lunar eclipse, not lunar eclipse, solar eclipse. Okay, so in this image here, these chromospheric features, the prominences that are over here and over here, you get this like pinkish looking color that comes from those 3 lines. If you mix together the red, the greenish blue, and the blue, mix that together, you get that color. So what you're seeing here is you're seeing emission lines. So once you absorb that light, hydrogen will eventually release the light. And so we're actually seeing the light being emitted from those from the atoms that originally absorbed light. And when you mix the 3 together, you get that color. So it's a very common color you see in space images. This pinkish purplish looking color, it comes from hydrogen. All right. Now, what's being shown in this picture in particular is the emission of light. So when you have an electron that's absorbed light, it will eventually release that energy. Okay. However, that's not a very predictable thing. Okay. In fact, the release of energy from these atoms is one of the truly random processes that exist in nature. When an electron is absorbed, so say we're talking about, this Balmer wavelength here. This is a very common wavelength, 656.3 nanometers. Okay, level 2 up to level 3. Okay, so if that wavelength gets absorbed, you move an electron from level 2. If there's a level 2 electron there, there may not be. But if there is one, it can be absorbed and go to level 3. And so a 656.3 nanometer wavelength of light is removed. And then what happens is that that electron eventually will de-excite. It will come down. And when it comes down, it will emit light. And it could emit that same wavelength out. Okay, but when it does, we have no idea when it happens. It's spontaneous. Okay, it happens rather quickly though. It happens within like a small fraction of a second. But to know exactly when it occurs, we don't know. In fact, I mean this laser light that I have for my clicker here, this is actually an emission. This is what's being seen here. It's emission, but it's controlled. That's what a laser is. Laser is an acronym. It stands for Light Amplified Stimulated Emission of Radiation. And it's controlled emission. What they do in here is they take, I don't know exactly what the substances that they're using here, but they excite the atoms all at once, and they have a means to de-excite them. They can actually control them being released. And so this is stimulated as opposed to being spontaneous. But most times in space it's kind of random. Now, I said here that when this electron absorbs that photon and goes to level 3, it will come down spontaneously. It has options. Okay? It will not release the same photon necessarily. When it comes down, it has the option to go level 2 or level 1. And it can go from level 2, then to level 1, or it can just skip level 2 and just jump right down to level 1. Okay? So if this photon gets absorbed and the electron jumps to level 3, it could go from level 3 down to level 1, and then it will actually emit this photon here, 102.6 nanometers. So the way it goes up is very predictable. Okay? The way it goes down is not as predictable. Okay? And so the dark lines that appear in spectrum are due to absorptions. Okay? A lot of bright colors that we see in nebula or emission lines. Okay? Like here, these lights up here, these are emission lines. This is this stuff here. Okay? A lot of the light here is due to mercury. Mercury's in the lights. And so a lot of the emission is due to mercury emission lines. The mercury has a bunch of emission lines that are in a really boring part of the spectrum. That's why these lights are dull and gives you weird moods because it's just like a beige almost. All right, so that's all I'm going to talk about for today as far as this stuff's concerned. Okay, let's spend the rest of the time talking about